Mid-February 1943,
This Sherman is in
Sidi Bou
remarkably good
Zid,
condition.
Tunisia. The M4A1
Its armor
Sherman
could pose
sat
a serious
motionless in
threat
the
if
desert
recaptured.
sand, its engine still warm, its American White Star insignia unblemished by the chaos that had engulfed the Faid Pass just hours earlier. German forces from the 10th and 21st Panzer Divisions had torn through American positions in what would become one of the most humiliating defeats suffered by United States forces in the entire war, destroying over 100 tanks and capturing thousands of prisoners in a rout that sent shockwaves through Allied command. But for the officers of Schwer Panzerabteilung 501, the heavy tank battalion equipped with the fearsome Tiger Ch, the real prize was not the tactical victory. It was this single American tank, captured intact and fully operational, abandoned by its crew during the retreat. If you found this story valuable, like helps us share more forgotten chapters of history with those who appreciate them. Subscribe if you'd like to see more. Each story we uncover matters, and your support makes it possible to keep these voices from the past alive. The Sherman bore markings identifying it as belonging to Company G.
If you found this story valuable, a like helps us share more forgotten chapters of history with those who appreciate them. Subscribe if you'd like to see more. Each story we uncover matters, and your support makes it possible to keep these voices from the past alive.
1st Armored Regiment, 1st Armored Division. Serial number USA 3267641, manufactured at Lima Locomotive Works in Ohio, one of 11 facilities across the United States producing M4 variants at rates that German intelligence found difficult to credit. The tank's name, painted in white letters on its olive drab hull, read War Daddy 2, the kind of personalization that American crews applied to vehicles they expected to keep for extended periods, a confidence that German tankers found almost quaint, given the attrition rates armored units typically suffered. Hauptmann Wilhelm Wessel, a technical officer attached to the battalion, conducted the initial inspection with the methodical precision that German military culture demanded. The tank showed no significant battle damage. Its 75mm M3 gun remained functional. The Continental R975 radial engine, a 9-cylinder air-cooled power plant derived from aircraft engine technology, started on the first attempt when German mechanics applied power to the electrical system. The tracks showed normal wear consistent with several hundred kilometers of operation. Every system appeared to function exactly as designed, which was precisely what troubled Wessel as he documented his findings. German tankers had grown accustomed to mechanical temperament in their own vehicles. The Panzer III and Panzer IV that formed the backbone of Wehrmacht armored forces required constant attention, their transmissions demanding careful rev matching and double clutching to avoid damage, their engines needing frequent adjustment of valve clearances and ignition timing. The Tiger I tanks of Schwer Panzerabteilung 501, the most powerful armored vehicles in the world, were mechanical prima donnas that consumed spare parts and maintenance hours at rates that strained logistics systems to their limits. German crews accepted these limitations as the natural cost of operating sophisticated military equipment. The captured Sherman suggested that American engineers had reached different conclusions about acceptable trade-offs. Higher command at the Army Weapons Office in Berlin had standing orders regarding captured enemy equipment of particular interest. This Sherman, one of the first intact examples to fall into German hands in the North African theater, qualified for comprehensive technical evaluation. The tank would be transported to Germany, to the proving ground at Kummersdorf, where Wehrmacht engineers could subject it to systematic testing that would reveal its capabilities, and perhaps its vulnerabilities. The journey from Sidi Bou Zid to the port of Sfax covered approximately 350 kilometers of North African terrain, desert tracks, damaged roads, mountain passes that would test any vehicle's mechanical stamina. German drivers from the reconnaissance unit assigned to deliver the Sherman approached the task with professional skepticism born of experience with their own equipment. They calculated fuel requirements, identified locations where recovery vehicles might be positioned if the tank broke down, and prepared contingency plans for the mechanical failures they considered inevitable over such a distance. The Sherman refused to cooperate with their pessimistic expectations. 4.5 days after departing Sidi Bou Zid, the captured tank rolled into Sfax under its own power, having covered the entire distance without a single mechanical failure that required stopping for repairs. The engine had maintained consistent operating temperature despite ambient conditions that caused German vehicles to overheat. The transmission had shifted smoothly through all 5 forward gears, without the grinding or hesitation that plagued German units operating under similar conditions. The final drives, the critical components that transferred engine power to the tracks, showed no signs of the stress that routinely disabled German tanks after extended road marches. German mechanics who accompanied the convoy documented their observations in reports that would eventually reach Kummersdorf. The American tank demonstrated automotive characteristics that contradicted assumptions German engineers had accepted about the necessary relationship between performance and reliability. It wasn't faster than German tanks, wasn't more heavily armed, wasn't better protected. It simply worked, consistently and without complaint, through conditions that would have degraded or disabled German equipment requiring constant attention. At Sfax, War Daddy II was loaded onto a cargo vessel for transport across the Mediterranean to Italy, then by rail to Germany. The journey would take several weeks during which German engineers at Kummersdorf prepared testing protocols designed to answer questions that the 350-kilometer drive had already begun to raise. How had American engineers achieved such reliability? What design principles explained the Sherman's mechanical resilience? And most troublingly, what did this single tank reveal about American industrial capabilities that German intelligence had consistently underestimated? The Kummersdorf Proving Ground occupied a sprawling complex approximately 25 kilometers south of Berlin, the primary facility where Wehrmacht technical branches evaluated both German developments and captured enemy equipment. The site had served German military research since the 1870s. Its test tracks, firing ranges, and engineering laboratories, hosting generations of weapons development from black powder artillery to rocket propulsion experiments conducted by a young Werner von Braun. By 1943, Kummersdorf's primary function had shifted to comparative evaluation, understanding how German weapons measured against those of enemies who, according to Nazi propaganda, should have been incapable of producing competitive military technology. War Daddy Teku arrived at Kummersdorf in early spring 1943, assigned the designation Versuchsfahrzeug 259 and German military license plate WH0589431. Test engineers had already stenciled armor thickness measurements across every surface of the tank, marking penetration angles and plate dimensions for the comprehensive evaluation program they had designed. Photographers documented every component from multiple angles. Draftsmen prepared technical drawings that would accompany written reports. The German military bureaucracy mobilized its considerable apparatus to understand this American machine. The initial inspection teams included specialists from multiple technical branches, each examining systems within their expertise. Powertrain engineers focused on the transmission, final drives, and engine. Armor specialists measured plate thicknesses and examined welding techniques. Weapons experts evaluated the 75mm gun, its stabilization system, and the turret traverse mechanism. Electrical engineers traced wiring diagrams and tested component reliability. The comprehensive approach reflected German thoroughness and the recognition that this tank might reveal more about American industrial philosophy than any intelligence report could convey. The transmission attracted immediate attention from engineers accustomed to the complex, temperamental gearboxes that German tanks employed. Where German designs used straight-cut gears requiring precise tolerances and generating the distinctive whine that tankers associated with armored operations. The Sherman transmission featured helical-cut gears, the herringbone pattern that distributed stress across multiple gear teeth simultaneously, rather than concentrating loads on single contact points. This design, standard in American automotive manufacturing since the 1920s and refined through decades of civilian production, provided exceptional durability with significantly reduced precision requirements during manufacturing. German engineers understood the theoretical advantages of helical gearing. They had chosen not to implement it in tank transmissions because German industry, despite its reputation for precision manufacturing, lacked the mass production capability to manufacture helical gears economically at the scale military requirements demanded. The cutting and grinding operations required for helical gear production demanded specialized machine tools and trained operators that German industry couldn't spare from other essential production. American industry, by contrast, had been manufacturing helical gears by the millions for civilian automobiles, developing production techniques that reduced costs while maintaining quality standards that German military specifications couldn't match. The synchronization system in the Sherman transmission represented another revelation that challenged German engineering assumptions. Gears 2 through 5 featured synchronizers that matched shaft speeds during shifting, eliminating the need for the double clutching technique that German tank drivers spent considerable training time mastering. American designers had assumed that ordinary soldiers with basic automotive experience would operate these tanks, that crews would include men who had driven civilian automobiles and trucks before entering military service. The transmission design accommodated this expectation, making gear changes nearly as simple as operating a civilian vehicle. German tank design proceeded from fundamentally different assumptions. Tanks were sophisticated military equipment that demanded extensive specialized training to operate correctly. Drivers learned complex techniques for matching engine and transmission speeds, developed sensitivity to the subtle sounds and vibrations that indicated proper shifting, and accepted that improper technique would damage components requiring repair or replacement. This approach might have been acceptable if German crews received adequate training time and if replacement parts remained available. By 1943, neither condition consistently applied. The Continental R975 radial engine, examined by propulsion specialists, demonstrated design philosophy differences that explained much about comparative reliability. The 9-cylinder air-cooled engine derived from aircraft powerplant technology, adapted for tank use with modifications that maintained its fundamental characteristics. Air cooling eliminated the vulnerability to coolant system damage that liquid-cooled engines suffered, and the radial configuration provided inherent balance that reduced vibration-induced stress on components. The engine's 400 horsepower output was adequate rather than exceptional, but its tolerance for varied operating conditions impressed engineers who had struggled with German tank engines that demanded constant adjustment. The air filtration system caught particular attention from engineers whose colleagues had documented German tank failures in North African conditions. Desert sand destroyed engines by entering through inadequate filtration, causing accelerated cylinder wear and bearing failure that left tanks stranded far from repair facilities. The Sherman's filtration system, designed with input from American automotive engineers experienced with dusty agricultural applications, handled fine particulate matter without the frequent cleaning or replacement that German systems required. War Daddy II had operated in Tunisia for months before its capture, yet its filters showed no signs of the degradation that disabled German vehicles within weeks of deployment to desert conditions. The testing program that unfolded through spring and early summer 1943 subjected the captured Sherman to systematic evaluation designed to quantify its capabilities across every measurable parameter. Engineers drove the tank through obstacle courses that replicated battlefield conditions, measuring fuel consumption, monitoring temperatures, and recording transmission behavior under varying loads. They conducted acceleration trials, hill climbing tests, and endurance runs that pushed the vehicle toward its design limits. After each trial series, they disassembled components to examine wear patterns, looking for evidence of stress, inadequate lubrication, or design weaknesses that combat might exploit. The results accumulated into a picture that contradicted everything German tank doctrine had accepted about necessary trade-offs between performance and reliability. The Sherman wasn't superior to German tanks in any single spectacular metric. Its armor was thinner than the Panther being prepared for production. Its gun was less powerful than the long 75mm weapons German engineers were fitting to upgraded Panzer IV variants. Its engine produced less power than the Maybach units destined for heavier German designs. In every category where German specifications excelled, the Sherman appeared adequate at best. But in the one category where German tanks consistently failed, operational endurance without maintenance intervention, the Sherman demonstrated capabilities that German vehicles couldn't approach. The captured tank completed extended trials covering hundreds of kilometers without requiring the maintenance stops that German test crews scheduled into every evaluation program as a matter of routine. Components that German experience suggested should show wear after 50 kilometers remained serviceable after 500. Systems that should have required adjustment maintained specification throughout testing periods that exceeded anything German vehicles could sustain. The final drive assemblies presented the starkest contrast between American and German engineering approaches. German Panther tanks, then entering production, employed final drive systems derived from Tiger I components, a configuration that proved catastrophically inadequate for the loads imposed by the Affenwünze 45-ton vehicle. Field reports from units operating Panthers documented final drive failures with disturbing frequency, sometimes occurring within 100 kilometers of leaving the factory. Tanks that survived their initial break-in period required constant monitoring, with mechanics listening for the distinctive sounds that preceded failure and commanders restricting tactical movements to preserve the fragile components for actual combat. The Sherman's final drives, built using the same helical gear principles as the transmission, showed no comparable vulnerability. Engineers at Kummersdorf drove the captured tank through trials that would have destroyed German components multiple times over. Yet the American final drives maintained consistent performance without adjustment or repair. The design margins built into these assemblies exceeded immediate requirements by factors that German engineers found extravagant, apparently wasteful allocations of material and manufacturing capacity that American designers clearly considered essential rather than excessive. Restoration specialists examining Sherman tanks decades after the war would discover final drives that required no mechanical work despite years of storage, testament to design margins that exceeded operational demands so substantially that time itself couldn't degrade them. German engineers in 1943 couldn't anticipate these future discoveries, but they could measure the performance differential that their testing revealed and draw conclusions about what it implied for comparative operational capabilities. By late spring 1943, preliminary reports from Kummersdorf had begun circulating through Wehrmacht technical branches. The documents, classified and restricted to senior officers and armaments ministry officials, presented findings that challenged comfortable assumptions about German technological superiority. The Sherman demonstrated what the reports termed American automotive engineering maturity, a phrase that acknowledged decades of civilian industry experience that Germany had never developed at comparable scale. The automotive disparity between nations reflected fundamental differences in pre-war economic development. The United States by 1941 had achieved automobile ownership rates that placed vehicles in the hands of ordinary citizens across economic classes. Mechanics who worked on family cars developed skills directly applicable to military vehicle maintenance. Factory workers who assembled automobiles understood mass production techniques that translated seamlessly to tank manufacturing. The entire industrial ecosystem had been optimized for producing reliable vehicles in enormous quantities, with quality control systems that maintained consistency across production runs, numbering in the tens of thousands. Germany had followed a dramatically different path. Automobile ownership remained concentrated among the wealthy and party elite. The Kraft durch Freud program, which had promised Volkswagen automobiles to German workers since 1934, had delivered fewer than 700 civilian vehicles by 1939, the promised people's cars absorbed by military requirements before most subscribers received their orders. German mechanics who worked on military vehicles often encountered automotive technology for the first time in military service, lacking the civilian experience that American counterparts brought to their assignments. This disparity in industrial maturity translated directly into tank design philosophy. American engineers built tanks that mechanics with civilian automotive training could maintain using skills they already possessed. Components derived from commercial production could be manufactured by workers experienced in similar civilian applications. The Sherman incorporated automotive industry standards wherever possible, leveraging existing supply chains and proven designs rather than requiring purpose-built military specifications for every component. German engineers built tanks that reflected their precision manufacturing heritage and assumption that specialists would maintain sophisticated military equipment. Components demanded tolerances that required skilled machinists working with quality materials. Maintenance procedures assumed trained technicians with years of specific military technical education. The approach produced vehicles with impressive specifications, but limited capacity for the sustained field operations that determined combat effectiveness over extended campaigns. The reports from Kummersdorf documented these observations with the systematic precision that German military culture demanded, but they offered no solutions that German industry could implement while simultaneously fighting a war that had already turned against the Reich. The lessons that American automotive excellence had to teach couldn't be learned quickly enough to affect vehicles already in production or designs already approved for manufacture. German engineers understood what they were seeing. They simply couldn't do anything about it. The captured Sherman at Kummersdorf, with its American star painted over and German crosses applied to its hull, represented more than enemy equipment brought home for technical examination. It was tangible proof that industrial maturity and practical manufacturing experience mattered more than theoretical engineering excellence or impressive performance specifications. Every kilometer the tank had driven without failure during testing was evidence that German tank design had prioritized the wrong characteristics. Every comparison between Sherman reliability and German vehicle performance revealed gaps that technical sophistication alone couldn't bridge. War Daddy II would continue serving as a test vehicle through 1943 and into 1944, its components disassembled, measured, and documented with exhaustive German thoroughness. Additional captured Shermans would arrive at Kummersdorf as German fortunes declined and American equipment fell into Wehrmacht hands through combat across multiple theaters. Each new specimen would confirm what the first comprehensive testing had revealed. American tanks weren't superior in firepower or protection, but they were fundamentally better engineered for the sustained operations that modern mechanized warfare demanded. The German officers who reviewed Kummersdorf's findings faced a conclusion that no amount of tactical skill or individual bravery could overcome. They weren't just facing American tanks in combat. They were facing American industrial philosophy, decades of automotive engineering experience, and manufacturing capacity that could produce reliable vehicles in quantities that German factories couldn't approach. The single Sherman captured at Sidi Bouzid had delivered a message that required no translation. Germany had already lost the industrial war, even as the military conflict continued its bloody course toward eventual defeat. June 6, 1943, Hillersleben Artillery Range, Saxony-Anhalt, Germany. Reichsminister Albert Speer stepped from his staff car into morning sunlight that cast long shadows across the proving ground where Germany's armored future would be demonstrated. The 38-year-old architect turned armaments minister had traveled from Berlin to preside over a conference that would bring together senior Wehrmacht officers, industrial leaders, and technical specialists to assess German tank development programs against captured enemy equipment. The demonstration program included comparative trials that Speer had specifically requested, direct performance comparisons that would reveal how German designs measured against the American tanks. His intelligence staff assured him were technically inferior. The vehicles assembled on the range represented Germany's armored ambitions and the captured evidence of Allied capabilities. A Panther Ausführung D, fresh from the MAN assembly line in Nuremberg, stood alongside the Tiger Hump that had established German armored supremacy through the fearsome reputation its 88mm gun and thick armor had earned on the Eastern Front. A Ferdinand tank destroyer, the massive 65-ton vehicle that mounted the devastating 80mm Pak 43 on a chassis originally designed for a rejected Tiger variant, represented German engineering's commitment to overwhelming firepower. And beside these German designs sat War Daddy II, the captured Sherman that Kummersdorf's testing had documented so thoroughly through the preceding months, its American origins still visible beneath the German crosses painted over its Allied insignia. Speer had studied the preliminary reports from Kummersdorf with the analytical precision that had made him effective as armaments minister despite his architectural training. The documents detailed American manufacturing techniques, compared reliability metrics, and documented automotive characteristics that German vehicles couldn't match. But reports were abstractions, numbers on paper that could be qualified, contextualized, or dismissed by officers committed to believing in German technical superiority. The demonstration at Hillersleben would make comparative capabilities visible in ways that reports couldn't convey. The testing program began with hill climbing trials on gradients specifically selected to stress powertrains under realistic combat conditions. Tank warfare rarely occurred on level ground. The ability to climb slopes, maintain traction on loose surfaces, and sustain power delivery through varying terrain conditions determined tactical flexibility that could mean the difference between exploiting opportunities and watching them pass. German doctrine emphasized the importance of terrain mastery, but doctrine assumed equipment capable of achieving it. The Sherman ascended first, its Continental R975 engine settling into the characteristic growl that American tankers associated with reliable power delivery. The driver, a German test operator who had spent weeks familiarizing himself with American control layouts and operating procedures, worked through the synchronized transmission with visible ease. Second gear for the initial acceleration. Third for the sustained climb. Fourth as the gradient decreased near the crest. The tank crested the hill without hesitation, its engine maintaining consistent temperature, its transmission shifting smoothly through each ratio, its tracks finding purchase on surfaces that would test any vehicle's capabilities. The Panther followed, its more powerful Maybach HL230 engine producing 700 horsepower, nearly double the Sherman's output, driving the 45-ton vehicle up the same gradient. The greater power-to-weight ratio should have produced superior performance. Theory suggested the Panther would climb faster, more confidently, demonstrating the engineering superiority that German designers had prioritized. Reality proved more complex. The Panther made the climb, but barely, and with considerably more difficulty than the lighter American vehicle had displayed. The transmission, which German crews had learned to treat with careful respect, required precise throttle management to prevent the lurching that accompanied rough shifts. The driver, experienced with German equipment, worked through the gears with technique refined through months of training. The double clutching and rev matching that American synchronizers had eliminated as requirements. The tank reached the summit, but observers noted the contrast between German struggle and American ease. Then came the Ferdinand. The 65-ton tank destroyer represented Germany's most ambitious armored vehicle project, mounting the powerful 88mm gun on a hybrid electric drive system that its designer, Ferdinand Porsche, had championed as the future of armored vehicle propulsion. The system used gasoline engines to generate electricity that powered electric motors driving the tracks, theoretically providing the smooth power delivery and precise control that traditional mechanical transmissions couldn't match. The Ferdinand had entered service just weeks earlier, rushed to the Eastern Front for Operation Citadel, despite engineering concerns that testing hadn't fully resolved. The Ferdinand began its climb with the electric whine that distinguished it from conventionally powered vehicles. Partway up the gradient, the whine changed pitch. The vehicle slowed, then stopped. Recovery crews moved forward as the Ferdinand sat motionless on the hillside, its crew reporting that the electrical system had overloaded, the drive motors overheating under sustained load. The embarrassment unfolded before dozens of senior officers and industrial leaders who had gathered expecting to witness German engineering excellence. Instead, they watched technicians struggle to restart a vehicle that represented years of development and enormous resource expenditure, defeated by a test that a captured enemy tank had passed without difficulty. Speer observed the failure with the calculating attention he brought to every armaments assessment. The Ferdinand's problems weren't news to engineers who had warned about the design's limitations, but witnessing the failure in person, in comparison with American equipment that simply worked, created impressions that technical reports couldn't convey. The incident would influence Speer's thinking about German armaments priorities for the remainder of the war, contributing to his growing conviction that German engineering had pursued impressive specifications at the expense of practical functionality. The aftermath of the Hillersleben demonstration produced assessments that circulated through German military and industrial channels with unusual frankness. Officers who had witnessed the comparative trials reported observations that contradicted comfortable assumptions about Allied capabilities. The Sherman's performance, while not spectacular in any single category, had demonstrated a consistency and reliability that German vehicles couldn't match. American engineering, dismissed in propaganda as the product of soft capitalists incapable of matching German precision, had produced equipment that outperformed German designs in the metrics that mattered most for sustained combat operations. Speer's own observations appeared in various forms over subsequent months and years, including memoirs written after the war that reflected on what German leadership had witnessed but failed to adequately address. He noted that reports on Sherman cross-country mobility had been very favorable, documenting the tank's ability to climb terrain that German experts had considered inaccessible to armored vehicles. He attributed this capability to the Sherman's power-to-weight ratio, which provided cross-country mobility on level ground that was definitely superior to German tanks. The 26th Panzer Division had specifically reported this advantage from Italian operations, where Shermans operated across mountainous terrain that immobilized heavier German vehicles. These observations, from Germany's armaments minister based on direct witnessing and field reports, carried weight that contradicted propaganda narratives about American industrial inferiority. The Sherman wasn't defeating German tanks through superior firepower or armor protection, categories where German specifications genuinely excelled. It was defeating them by arriving at the battlefield in operational condition and completing missions that German mechanical failures prevented. Public acknowledgement of American capabilities appeared, carefully worded, in the June 27, 1943 edition of Das Reich, the weekly newspaper that served as a propaganda vehicle for the regime. The article described the Sherman as one of the special accomplishments of the North American laboratories, calling it quite a praiseworthy product of the North American steel industry. The piece noted that the first things to attract attention were serial construction and fulfillment of the almost arrogant requirements of the North American automobile industry. The gyro-stabilized gun received mention as the first attempt of its kind ever to be made anywhere, acknowledging American innovation in technology that German tanks lacked entirely. These public statements, sanitized for propaganda purposes to avoid appearing defeatist, nevertheless represented admissions that German technical superiority was not as absolute as ideological commitments demanded. The language revealed anxiety beneath the confident surface, acknowledgement that American industry had produced equipment worthy of respect, despite years of propaganda dismissing American capabilities as products of decadent capitalism incapable of matching German engineering excellence. Back at Kummersdorf, systematic testing continued through summer and autumn of 1943, expanding to include additional Sherman variants as more captured vehicles reached German hands. Engineers documented operational ranges that confirmed preliminary findings. the Sherman demonstrated the ability to operate for distances exceeding 2,000 kilometers before requiring major maintenance intervention, approximately 4 times what early production Panthers achieved under field conditions before breakdown. The comparison was devastating for German planning assumptions that couldn't accommodate such disparity. Transmission efficiency testing quantified advantages that field observations had suggested. Power losses through the Sherman drivetrain measured significantly lower than comparable German systems, meaning more of the engine's output actually reached the tracks to propel the vehicle. The synchronized gearing that eliminated double clutching requirements also reduced the mechanical shock that damaged German transmissions when operators shifted improperly or hastily under combat stress. American design had anticipated that combat conditions would produce exactly the rough handling that German equipment couldn't tolerate. The final drive examinations continued revealing German engineering weaknesses that field units had documented with increasing alarm. Panther final drives, derived from Tiger I components inadequate for the 45-ton vehicle's demands, failed with disturbing regularity across every theater where the tanks operated. German mechanics developed listening skills to detect the sounds that preceded catastrophic failure, pulling vehicles from service when subtle noises suggested impending breakdown. The approach might preserve individual tanks, but couldn't address fundamental design inadequacies that made such vigilance necessary. Field reports from Panther units quantified reliability problems in terms that operational planners couldn't ignore. During Operation Citadel at Kursk in July 1943, the massive armored offensive that was supposed to demonstrate German armored supremacy, Panther operational readiness had collapsed to 16%. Mechanical failures eliminated more tanks than Soviet anti-tank fire. Units that should have spearheaded the offensive instead struggled to field enough operational vehicles for meaningful combat contribution. The Panthers that did fight performed impressively, their powerful guns and thick frontal armor proving effective against Soviet armor. But too few reached the battlefield to affect operational outcomes. Monthly readiness reports traced gradual improvement as manufacturers addressed the worst design deficiencies and production quality stabilized. December 1943 showed 37% operational readiness. February 1944 reached the same figure. April 1944 achieved 50%. May 1944 finally reached 78%, presented in German reporting as evidence of successful problem-solving. These figures, treated as accomplishments within Wehrmacht planning circles, merely brought Panther reliability to levels the Sherman had achieved from initial production in 1942. German engineering was celebrating reaching standards that American tanks had exceeded from the beginning. The progression illustrated fundamental differences in development philosophy that explained why German tanks required years to achieve reliability American designs delivered immediately. German engineering culture prioritized performance specifications, speed, armor protection, firepower, that looked impressive in technical documentation and satisfied military requirements emphasizing individual vehicle superiority. Reliability was treated as a secondary consideration that could be addressed through production refinements after initial deployment revealed problems. American automotive engineering, shaped by decades of civilian industry competition, where reliability directly affected sales and reputation, approached vehicle development from opposite priorities. The Sherman's designers had included engineers from General Motors, Ford, and Chrysler, who understood that customers, whether civilian car buyers or military procurement officers, would reject vehicles that required constant maintenance and frequently broke down. Reliability wasn't a feature to be added after the fact. It was a fundamental requirement that shaped every design decision from initial concept through production. The manufacturing philosophy difference extended to component sourcing and parts interchangeability that determined whether damaged vehicles could be returned to service or had to be written off. Sherman transmissions came from multiple manufacturers: Caterpillar Tractor, Buick Motor Division, Ford Motor Company. all building to identical specifications with fully interchangeable parts. A transmission manufactured in Detroit could be installed in a tank originally equipped with a transmission from Peoria without adjustment or modification. This standardization, routine in American automotive practice, remained largely theoretical in German tank production. German tank manufacturers each introduced subtle variations that prevented true parts interchangeability, even within nominally identical vehicle types. A final drive from one Panther manufacturer might not fit vehicles produced by another without modification. Replacement components had to be tracked by manufacturer origin and matched to vehicles from the same source. The logistics complexity this created overwhelmed German supply systems that were already straining to deliver parts across extended front lines, stretching from Norway to North Africa to the depths of Russia. General Heinz Guderian, Inspector General of Panzer Troops and architect of German armored doctrine, monitored reliability reports with growing concern through late 1943 and into 1944. His official communications reflected optimism appropriate to his position while acknowledging problems that field units reported with increasing urgency. A March 1944 message noted that improvements to Panther reliability had achieved acceptable standards, with engine life reaching 700 to 1,000 kilometers, figures that represented genuine progress from the catastrophic early failures, but still lagged far behind American capabilities. Guderian understood what the reliability disparity meant for operational planning. German armored doctrine emphasized concentration of force for decisive breakthrough operations that would shatter enemy defenses and create exploitation opportunities. This doctrine assumed that concentrated forces would be available when needed, that tanks would reach assembly areas in operational condition, that units wouldn't be degraded by mechanical attrition before combat even began. The reliability gap made these assumptions increasingly questionable. American armored units could conduct road marches of hundreds of kilometers with confidence that vehicles would arrive, functional at their destinations. German units had to calculate that every kilometer of movement consumed precious mechanical endurance, that road marches might eliminate as many vehicles through breakdown as subsequent combat would through enemy action. The operational flexibility that reliable equipment provided American commanders simply didn't exist for their German counterparts, who had to husband limited mechanical resources for moments when combat was absolutely necessary. The comparative testing program expanded through 1943 and 1944 as additional captured vehicles reached Kummersdorf. British forces in Italy lost Shermans to German capture, some modified with the 17-pounder anti-tank gun that created the Firefly variant addressing the Sherman's main armament limitations. Soviet forces on the Eastern Front received thousands of diesel-powered M4A2 Shermans through Lend-Lease, and retreating German units captured significant numbers as the front lines shifted westward. Each captured vehicle underwent testing protocols that confirmed and extended findings from War Daddy 2. The British Firefly variants attracted particular attention from German engineers examining growth potential built into original designs. The Sherman's turret ring, dimensioned generously in the original specification, accommodated the significantly larger 17-pounder gun with minimal modification. A new mantlet, revised ammunition storage, and minor hull changes that British workshops accomplished without disrupting American production. The Firefly demonstrated that American designers had built upgrade capacity into their vehicle that German engineers hadn't considered when specifying their own tanks. The Panther, rushed into production to counter Soviet T-34 tanks, had no comparable capacity for significant armament upgrades. Its turret ring dimensions, optimized for the existing 75mm caliber K-42 gun, couldn't accommodate larger weapons without complete turret and hull redesign. The tank that was supposed to restore German armored superiority had reached its developmental ceiling before production was fully established, while the inferior American design retained potential for improvements that would keep it competitive through the war's end and beyond. The diesel-powered M4A2 Shermans captured from Soviet forces impressed German engineers who examined them at Kummersdorf. The twin General Motors 6246 diesel engines provided performance-matching gasoline variants while consuming substantially less fuel, a critical advantage as German fuel supplies dwindled under Allied bombing and the loss of Romanian oil fields. German designers had experimented with diesel tank engines, but abandoned the effort due to manufacturing difficulties with fuel injection systems that required precision machining. German industry couldn't sustain at scale. American industry produced diesel Shermans alongside gasoline variants without disrupting production schedules, demonstrating manufacturing flexibility and technological sophistication that German industry couldn't match under wartime conditions. The contrast highlighted how American industrial depth, the ability to pursue multiple design approaches simultaneously while maintaining production volumes, created options that German resource constraints precluded. By early 1944, the accumulation of testing data and field reports had built an undeniable picture of comparative capabilities that German technical branches could no longer rationalize away. The Sherman wasn't just an adequate tank that American production capacity made numerous. It was a fundamentally better engineered vehicle for sustained field operations, designed by engineers who understood that reliability determined combat effectiveness more than impressive specifications that couldn't be maintained under battlefield conditions. The reports documented these findings with German precision, circulating through channels where officers who needed to understand capabilities could access them. But understanding and acting were different challenges entirely. German industry lacked the capacity to redesign production around reliability principles while simultaneously fighting a war that was consuming resources faster than they could be produced. The knowledge that Kummersdorf's testing provided couldn't translate into improved equipment quickly enough to affect the war's trajectory. The Sherman's advantages would only become more pronounced as the war continued, as German quality control degraded under bombing and labor shortages, as supply lines stretched and broke, as the industrial disparity that Kummersdorf's testing had revealed expressed itself in operational outcomes that no amount of tactical skill could overcome. The tank that German propaganda had dismissed as the product of inferior American engineering would outlast, outperform, and ultimately overwhelm the sophisticated German designs that had consumed so much engineering effort and industrial capacity. War Daddy the Seku and its fellow test subjects at Kummersdorf had delivered their verdict on comparative industrial philosophies. German engineers recorded that verdict in meticulous technical documentation. They understood its implications with professional clarity. They simply couldn't do anything about it in time to matter. April 27, 1944, 11:47 p.m., Friedrichshafen, Germany. The first Pathfinder flares descended over the industrial complex, where Maybach Motorenbau GmbH manufactured the engines that powered Germany's most formidable tanks. Royal Air Force Bomber Command had dispatched 322 aircraft, Lancaster and Halifax heavy bombers carrying high explosive and incendiary loads, to attack what British intelligence had identified as a critical choke point in German armored vehicle production. The Maybach facility produced the HL-230 engines installed in Panthers and Tigers, power plants that required precision manufacturing capabilities concentrated in this single location. Adjacent to the engine plant stood the Zahnradfabrik Friedrichshafen Works, manufacturer of the transmissions and final drives that mated to those engines. Two facilities, one raid, and the potential to cripple German tank production for months. The bombers released their ordnance through scattered cloud cover, navigation guided by electronic systems that had transformed area bombing into something approaching precision attack. High explosives cratered factory floors and collapsed roof structures. Incendiaries ignited fires that spread through machine shops, where irreplaceable tooling had taken years to accumulate. Secondary explosions marked the destruction of finished components awaiting shipment. By morning, reconnaissance aircraft confirmed what planners had hoped. Both facilities had suffered catastrophic damage that would halt production entirely. The Maybach ZF raid, described in Imperial War Museum archives, as the most damaging attack on German tank production of the entire war, achieved effects that rippled through Wehrmacht armored forces for the remainder of the conflict. Engine and transmission production ceased completely. The halt lasted not weeks, but 6 months, as German industry struggled to repair facilities, replace destroyed tooling, and train workers to operate rebuilt production lines. When manufacturing finally resumed in November 1944, quality control had degraded to levels that introduced new categories of failure into vehicles already struggling with reliability problems. The contrast with American tank production could not have been starker. Sherman engines came from multiple manufacturers operating facilities dispersed across the continental United States, far beyond the reach of any Axis bombing capability. Continental Motors produced the R975 Radial in Detroit. Ford manufactured the GAA V8 at its River Rouge complex. General Motors built the twin-diesel 6046 at facilities in Michigan and Indiana. Chrysler assembled the A57 multibank engine, 5 6-cylinder automobile engines geared to a common output shaft, at plants that continued civilian production alongside military contracts. The destruction of any single facility would have inconvenienced American tank production. It would not have halted it. The Friedrichshafen raid's aftermath introduced complications that compounded existing reliability problems through mechanisms German engineers hadn't anticipated. Slave laborers, increasingly employed in German war production, as German workers were conscripted for military service, recognized opportunities for sabotage that didn't require dramatic acts of resistance. Cigarette filters jammed into oil passages would cause bearing failures after hundreds of kilometers of operation, long after the vehicles had left factory inspection. Gaskets installed incorrectly would leak gradually, degrading lubrication until catastrophic failure occurred far from any repair facility. Components assembled without proper clearances would wear prematurely, creating maintenance requirements that German field logistics couldn't address. These sabotage effects never threatened Sherman production. American workers, earning good wages under conditions that bore no resemblance to forced labor, had every incentive to produce quality equipment. Many had sons, brothers, or husbands serving in armored units that would operate the tanks they built. The social contract underlying American war production, patriotic motivation reinforced by economic reward, generated quality control that coercion could never replicate. German field reports from late 1944 documented accelerating mechanical failures that exceeded even the problematic rates from earlier production periods. Panthers that had required careful handling to survive 500 kilometers now broke down within 200. Transmissions that had previously reached acceptable service intervals now failed during the break-in period. Final drives that design modifications had supposedly corrected reverted to failure modes that had plagued initial production. The Friedrichshafen raid had destroyed more than buildings and machinery. It had disrupted the institutional knowledge and quality systems that had gradually improved German tank reliability through 1943 and early 1944. The operational consequences of the reliability gap manifested across every theater where German and American armored forces engaged. In Normandy, following the June 1944 Allied invasion, German armored units faced logistics challenges that their American counterparts simply didn't experience. Panthers required rail transport for movements exceeding 100 kilometers because their final drives couldn't survive sustained road marches. Field commands issued explicit orders restricting Panther operations to preserve the vehicles for actual combat, rather than consuming their mechanical lives in approach marches. The tactical inflexibility this created, the inability to concentrate armored forces rapidly in response to developing situations, ceded initiative to American commanders whose tanks could move freely. American armored units operated under fundamentally different constraints. Tank battalions conducted road marches of hundreds of kilometers, confident that vehicles would arrive operational at their destinations. Maintenance requirements existed, but they fit within predictable schedules that logistics planning accommodated. A Sherman battalion could execute orders to relocate 50 miles and arrive ready for combat operations within hours. A Panther battalion receiving identical orders had to calculate whether the movement alone might eliminate vehicles needed for the subsequent mission. The Berg Panther armored recovery vehicle, built on the Panther chassis specifically to recover disabled Panthers from the battlefield, illustrated German awareness of reliability problems and the inadequacy of German solutions. The recovery vehicle shared the same powertrain as the tanks it was supposed to rescue, meaning Berge Panthers suffered identical breakdown rates. German units reported recovery vehicles disabled while attempting to reach disabled tanks, creating cascading maintenance failures that consumed resources without returning combat capability to the force. American recovery operations proceeded from different assumptions entirely. The M32 tank recovery vehicle, based on the Sherman chassis, shared its parent vehicle's reliability characteristics. It could reach disabled tanks and return them to maintenance facilities without becoming a maintenance problem itself. More importantly, American doctrine assumed that damaged vehicles could often be repaired with parts and skills available at field maintenance units. German repairs frequently required evacuation to rear area facilities with specialized equipment that forward units didn't possess. The 10th SS Panzer Division's experience with captured Shermans demonstrated German recognition of American reliability advantages in the war's final months. During Operation Nordwind in January 1945, German forces captured 12 M4A3 Shermans from the American 43rd Tank Battalion at Hillersleben. The tanks fell into German hands intact when their crews abandoned them during the German assault. American crews trained to disable captured equipment had been overwhelmed too quickly to follow procedures. The 10th SS Panzer Division formed these captured Shermans into the 13th Company of its Panzer Regiment, pressing them into immediate combat service without modification. German crews, experienced with their own equipment's limitations, quickly recognized what Kummersdorf testing had documented years earlier. The American tanks simply worked, starting reliably in the bitter January cold that immobilized German vehicles with frozen engines and bulky transmissions. The Shermans served through the remaining months of the war, functioning as reconnaissance vehicles and mobile reserves, roles requiring sustained movement without maintenance stops and consistent mechanical performance that German equipment couldn't provide. The 150th Panzer Brigade, formed specifically for infiltration operations during the Battle of the Bulge in December 1944, sought captured American vehicles for missions requiring mechanical reliability behind enemy lines. German planners understood that infiltrators operating far from support couldn't risk the breakdowns that characterized German equipment. Only American vehicles offered reasonable assurance that mechanical failures wouldn't compromise operations before they achieved their objectives. The brigade received only 2 Sherman tanks, despite extensive efforts to obtain more, and only one proved serviceable enough for operations. Even this single vehicle never saw combat. Massive traffic jams prevented the infiltration operation from achieving its objectives before the overall German offensive stalled. But the planning assumption was revealing. German military professionals, planning operations where reliability was literally a matter of life and death, specified American equipment as essential rather than German vehicles that couldn't be trusted. January 23, 1945 brought official documentation of German mechanical failure reaching crisis proportions. The Panzer Commission, responsible for coordinating German armored vehicle development and production, convened a meeting that produced reports circulated to senior Wehrmacht leadership. The findings, preserved in German military archives, documented failures across every category of armored vehicle production. General der Panzertruppe Wolfgang Thomale, Chief of Staff to the Inspector General of Panzer Troops serving under Guderian, presented statistics that quantified the catastrophe. Prior to the 1945 Eastern Offensive, German armored forces reported 500 defective final drives in the Panzer IV, the workhorse medium tank that had served since 1939 and should have been thoroughly debugged after years of production. 370 Panther final drives had failed. Approximately 100 Tiger final drives were out of service. 200 additional failures had been reported in the Hetzer tank destroyer, based on the Czechoslovak 30th T chassis that German forces had employed since 1939. These figures represented vehicles already at the front, supposedly operational and available for combat, yet incapable of maneuvering due to failed drivetrain components. Tomali explained the operational impact in terms that even non-technical officers could understand. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles and in some situations abandoned whole vehicles just because of final drive problems, fearing they would be stranded and captured. German tankers were abandoning their vehicles not because of enemy action, but because they couldn't trust the machines to carry them away from danger. The psychological dimension of mechanical unreliability, the constant awareness that breakdown might deliver crews into enemy hands, degraded combat effectiveness in ways that couldn't be quantified, but were nonetheless real. American tankers faced many dangers, but fear that their vehicles would betray them through mechanical failure wasn't among their primary concerns. The production statistics that framed these reliability problems told the war's industrial story in numbers that required no interpretation. American factories produced 49,234 Sherman tanks during the war, more than total German production of all tank types combined across the entire conflict. German industry, despite prioritizing armored vehicle production and diverting resources from other military requirements, managed approximately 24,000 tanks of all types. The quantitative disparity was roughly 2-to-1, but the effective disparity was far greater when reliability factored into calculations of available combat power. A Sherman that operated 30 days per month contributed 30 tank days of combat capability. A Panther that operated 12 days per month due to maintenance requirements contributed less than half that figure. American forces possessed not just twice as many tanks, but tanks that were available for combat twice as often, creating an effective superiority ratio approaching 4-to-1. These calculations didn't include the logistics burden that unreliable vehicles imposed on German forces. Every broken-down Panther required recovery assets, maintenance personnel, spare parts, and transportation capacity that could have supported operational vehicles. Every evacuation consumed fuel that could have propelled combat operations. The German logistics system, already strained beyond sustainable limits, hemorrhaged resources supporting vehicles that couldn't contribute to combat operations. American logistics operated from opposite premises. Reliable vehicles required less support infrastructure per tank. Standardized parts reduced inventory complexity. Maintenance procedures that ordinary soldiers could perform eliminated dependence on specialized technicians. The system that had produced the Sherman also produced the support structure that kept Shermans operational and did both more efficiently than German industry managed with its more sophisticated but less practical designs. The Lend-Lease dimension extended American industrial philosophy to Allied forces who received Sherman tanks in quantities that transformed their armored capabilities. The Soviet Union received 4,102 M4A1 diesel-powered Shermans through Arctic convoys and Pacific routes. Tanks that Soviet crews praised for reliability, characteristics their domestic T-34s didn't match, despite that vehicle's legendary reputation. British and Commonwealth forces received thousands of Shermans that equipped entire armored divisions, replacing British designs that couldn't be produced in adequate numbers. Chinese forces in Burma operated Shermans against Japanese armor that was technologically inferior to both American and German designs. Every theater where Shermans served confirmed what Kummersdorf testing had revealed. American automotive engineering produced vehicles that functioned under conditions that would disable more sophisticated competitors. Soviet mechanics, accustomed to the T-34's agricultural simplicity, found even the complex Chrysler A57 multibank engine easier to troubleshoot than many Soviet power plants. British crews, experienced with unreliable British tanks that had hindered North African operations, considered the Sherman a revelation in mechanical consistency. The war's final months provided conclusive demonstration of reliability's operational importance. As German forces retreated toward the Reich's shrinking borders, mechanical failures eliminated more armored vehicles than enemy action. Units reported that 70% of tank losses resulted from breakdowns rather than combat damage. Vehicles abandoned because they couldn't be repaired in time to escape advancing Allied forces. Tanks destroyed by their own crews to prevent capture when mechanical failures left them stranded. Kummersdorf itself prepared for evacuation in early 1945 as Soviet forces advanced toward Berlin. Engineers packed testing data and shipped documentation westward, hoping to preserve technical intelligence for whatever Germany might become after inevitable defeat. Some captured vehicles, including Shermans that had served as test subjects, were pressed into improvised combat service with units desperately defending the approaches to the capital. These tanks fought alongside German designs in the final desperate battles, providing one last comparison under actual combat conditions. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel supplies exhausted. The German vehicles, Panthers and the few remaining Tigers, broke down at rates that shocked crews accustomed to unreliability, but not to the complete mechanical collapse that characterized final months' production. The comparison needed no documentation. Everyone who witnessed it understood what it meant. Post-war analysis by American and British intelligence organizations confirmed what German testing at Kummersdorf had revealed and combat experience had demonstrated. Systematic examination of destroyed German tanks found mechanical failures as common as combat damage among causes of loss. Final drives broken from stress, transmissions seized from inadequate lubrication or operator error, engines burned out from overheating or oil starvation. The evidence, scattered across European battlefields in the wreckage of vehicles that had consumed enormous engineering effort and industrial resources, proved that German design philosophy had prioritized the wrong characteristics. The lessons influenced military-industrial thinking for generations. When West Germany began rebuilding military capabilities in the 1950s, designers consciously rejected the philosophy that had produced Panthers and Tigers. The Leopard 1 main battle tank, developed for the Bundeswehr, emphasized reliability and maintainability over pure performance specifications. Engineers studied American automotive principles and deliberately applied them to military vehicle development. The resulting tank incorporated design philosophies that had made the Sherman successful. Robust powertrains with substantial margins, easy maintenance requiring minimal specialized tools, standardized components enabling rapid field repairs, and growth potential allowing future upgrades without complete redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. Its success validated the lessons that Kummersdorf testing had taught, and that German industry couldn't implement while fighting a war it was already losing. Reliability wasn't a secondary consideration to be addressed after deployment revealed problems. It was the foundation upon which operational effectiveness depended, the characteristic that determined whether vehicles contributed to combat or consumed resources without return. War Daddy II, the captured Sherman that had begun the systematic comparison between American and German tank engineering, represented far more than enemy equipment subjected to technical examination. It was tangible evidence that industrial maturity and practical manufacturing experience mattered more than theoretical engineering excellence or impressive performance specifications. The single tank captured in Tunisia and tested exhaustively at Kummersdorf told the entire story through mechanical reliability that German designs couldn't match. Every kilometer driven without failure demonstrated that German tank design had followed a fundamentally wrong path. Every test confirming American automotive excellence proved that decades of civilian manufacturing experience produced capabilities that military-industrial mobilization alone couldn't replicate. Every comparison between Sherman reliability and German vehicle performance revealed gaps that no amount of engineering sophistication could bridge, while Germany simultaneously fought enemies on multiple fronts, with resources that shrank monthly under Allied pressure. The mathematics of armored warfare ultimately reduced to simple calculations that didn't require engineering expertise to understand. A tank that reliably reached the battlefield was infinitely more valuable than a tank with superior specifications that broke down before engaging the enemy. A battalion with 80% operational availability could execute missions that a battalion with 40% availability couldn't attempt. Industrial capacity that produced 50,000 reliable tanks would defeat industrial capacity that produced 25,000 unreliable tanks, regardless of which individual vehicles looked more impressive on specification sheets. German engineers at Kummersdorf understood these truths by mid-1943, documenting their findings with meticulous precision in reports that circulated through Wehrmacht technical channels. They had measured American advantages with scientific rigor. They had tested the evidence repeatedly, confirming conclusions that challenged comfortable assumptions about German technological superiority. They had reached the correct assessment of industrial realities that would determine the war's outcome. Understanding the problem and solving it were fundamentally different challenges. German industry lacked the capacity to transform its approach to tank design while simultaneously producing the vehicles that combat consumed. The knowledge that American reliability derived from decades of civilian automotive experience couldn't be replicated in the years remaining before Allied forces would overrun German factories. The institutional changes required to prioritize reliability over specifications would have disrupted production that couldn't be interrupted regardless of the quality problems that continuation perpetuated. The captured Sherman at Kummersdorf delivered a verdict that German engineering culture didn't want to accept but couldn't refute. American industry hadn't just outproduced German industry. It had out-engineered it in the ways that mattered most for sustained military operations. The tank that German propaganda dismissed as the product of inferior American capitalism had been designed by engineers who understood what determined combat effectiveness, manufactured by workers with skills developed through civilian experience, and supported by logistics systems that American industrial depth made possible. War Daddy 2 sat in German testing facilities as evidence of truths that no amount of ideological commitment could change. The war would continue for 2 more years after its capture, consuming millions of lives and destroying nations. But the industrial verdict had already been delivered in the spring of 1943, documented in German testing reports, confirmed by every subsequent comparison, and ultimately validated by the outcome that those comparisons had made inevitable. The Sherman tank didn't win World War II through superior firepower or heavier armor. It won through industrial philosophy that understood reliability was not a luxury but a necessity, that maintenance requirements determined operational availability, that vehicles which functioned when needed were infinitely more valuable than vehicles with impressive specifications that couldn't be sustained under combat conditions. German engineers at Kummersdorf proved this beyond reasonable doubt. German industry simply couldn't respond to proof that arrived too late to change anything that mattered.